In Chapter 11, we're going to talk about static aeroelastic and trim analysis. First, we're going to talk about the theory behind this trim analysis. The trim analysis solves a set of unknown trim variables and trim degrees of freedom for the balance of the 6 degrees of freedom forces and moment about CG between the aerodynamic and the inertial force. In other words, when you integrate aerodynamic, the difference between the aerodynamic and inertial loads about the CG, the net force and moment should be zero. The trim variables can be expressed as uh, uh, any device or any parameters which can change the aerodynamic forces can be defined as a trim variable. For example, the angle of attack, the side slip angle, the roll rate, pitch rate, and yaw rate, and the control surface deflections. The trim degrees of freedom vector contains the acceleration and the CG of the aircraft. So we have 6 degrees of freedom. So nx, ny, and z, p dot, q dot, r dot. And so the acceleration can induce inertial force. And so if we take the net force between the aerodynamic, the distributed aerodynamic forces and the inertial force, and apply to the structure where kgg is the stiffness matrix, then we can obtain the structure deformation. So when you integrate, and if you pre-multiply this equation by the rigid body mode, and so rigid body mode times the kgg is zero because the rigid body modes cannot produce internal loads. And so, in other words, if we integrate the difference between the aerodynamic forces and inertial force about CG, we will get a zero net force and moments. And how do we calculate the distributed aerodynamic force vector? This force can be expressed by the aerodynamic forces on the rigid aircraft and also the aerodynamic, so-called incremental aerodynamic feedback force. Why we call it feedback force? Because once the structure deforms, it will induce additional aerodynamic forces. Okay, and how can we calculate this incremental aerodynamic feedback force due to structure deformation? We can use the AIC matrix. We pre and post AIC matrix by the spline matrix and times dynamic pressure, and we call this matrix as a AIC bar. So once we have structure deformation from AIC, we can calculate this incremental aerodynamic feedback force. And the aerodynamic force on the rigid aircraft, which is a function of the trim variables, and we can do a Taylor's expansion. We expand this force on the about the mean flow, and the partial F partial A contains the distributed aerodynamic force derivatives with respect to the trim variable. Okay, so this is nothing but a first order Taylor's expansion. And how can we calculate partial F partial A? If we have AIC matrix, we can multiply to the rigid body mode, and the phi c is the aerodynamic control surface kinematic mode. And to this, we can calculate the partial F and the partial A. And F naught is the K-set aerodynamic forces at the mean flow condition. We call it thickness. Thickness. Later on, we're going to talk about how do we define trim variables. One of the trim variable we call can be defined called thickness. That's due to the thickness and camber of the configuration and the mean angle of attack, mean side slip angle, and mean control surface deflection. In other words, those alpha naught, beta naught, and delta naught are specified in the aerogen card. So when you specify specify those parameters in aerogen count, that defines our the mean flow. And so the treatment analysis calculate the perturbed aerodynamic trim variables about a mean flow. And how do we calculate the distributed inertial force? We have inertial force Fi, and we have a mass matrix, GZ mass matrix, times x double dot. X double dot is the structure acceleration, and the u double dot is the acceleration at CG. Okay, and we assume x double dot to be 0 because the trim analysis is a static area elastic problem and does not involve the structure acceleration. If x double dot is considered, the response of the aircraft becomes a dynamic loads problem. And u double dot can be related to the trim degree of freedom by the rigid body modal matrix. So if we know the acceleration at CG, we multiply by the rigid body mode, and we can get acceleration at all the GZ degrees of freedom. So we substitute this equation back to that equation, we can calculate the the inertial force by this equation. So mgg times rigid body mode times acceleration at CG. So to perform trim analysis, normally we need to import the GZ mass matrix using the assign matrix equal executive control command. So we can substitute this equation and this equation and that equation back to this equation, and we can construct this equation. Okay, and then we assume the structural deformation can be superimposed by the elastic mode times the generalized coordinate of the elastic mode QE. Why we only include the elastic mode? Because the rigid body modes cannot produce internal loads in the structure. That's the reason we only express X as a superimpose of all the elastic modes. For the whole aircraft structure, normally the lowest 50 or 100 elastic mode are sufficient to achieve a converged solution. So we can plug this equation to that equation. Then we pre-multiply this equation by a rigid body mode transpose. So the first term is field R transpose times kgg and times phi e times qe, and this term is 0 because the rigid body mode and elastic mode are orthogonal to the GZ mass matrix, and phi rr is the mgg pre and post multiplied by the rigid body mode. So this is the 6x6 rigid body mass matrix, and then next we pre-multiply this equation by the elastic transpose of the elastic mode, and this the first term is the kgg and pre and post multiplied by the elastic mode is the generalized stiffness matrix of the elastic mode, and the second term is a mgg pre and post multiplied by the rigid body mode and elastic mode, which is 0 because the elastic mode and rigid body mode are orthogonal to the mgz mass matrix. And QEE is the AIC bar, and the pre and post multiplied by the elastic mode. So after that, you can see we can invert this matrix. KEE minus Q infinity times QEE, we inverse that. Then we can plug the QE into this equation. So we can combine two equations, end up we only have one equation. And this equation in general can be expressed by this equation, which is MRR times Q UR double dot, which is a solution at CG, times F bar times the trim variables plus F naught. F naught is the mean flow distributed forces. So F FR can be expressed by this equation. F naught can be expressed by this equation. And A bar here, it can be expressed by this equation. Is a so-called aeroelastic amplification matrix. Okay, if we assume there is a no aeroelastic effect, which we set A bar to be 0, then you can see the FR is a phi R transpose times the spline matrix times partial F partial A, which is the aerodynamic stability derivatives of the trim variable. So the first row of this matrix is a CD alpha, CY alpha, CL alpha, and the rolling moment derivative with respect to alpha, and PG moment derivative with respect to alpha, and so on. The second one is the derivative with respect to beta. And then if we put A bar back, then this is the aerodynamic stability derivatives of the trim variable, including static aeroelastic effect. The F naught bar here, if we put A bar to be 0, is nothing but all the aerodynamic force and moment coefficients for the mean flow. Again, the mean flow we define is in the aerojet. Okay. Then if we put A bar back, and this is the mean flow distributed aerodynamic forces due to mean flow, including static aeroelastic effect. Okay, in this equation, we can split UR double dot and A into a given set and unknown set. So we can where sub G is given, sub U is unknown, and we can put all the unknown term in the left hand side, all the given term on the right hand side. Now, if we can invert this matrix, and then because all the terms on the right hand side are given, and we can solve the unknown trim degrees of freedom and the trim variables. So because in this equation A bar involve the inverse of this matrix, so and and this matrix becomes singular if the dynamic pressure reaches the lowest real eigenvalue of the matrix. So lambda lowest is so-called the divergence dynamic pressure at which the structure encounters the so-called divergence problem. So prior to the trim analysis, the trim module always calculate the lambda lowest and compare to the input dynamic pressure. If the lambda lowest is lower than the input dynamic pressure, it's a fatal error. Okay, so because the structure already encounter so-called the divergence problem, and we cannot solve the trim problem. So for supported structure, lambda lowest agrees with the divergence analysis. The divergent dynamic pressure are calculated by the G method flutter analysis. For free structure, the divergence dynamic pressure calculated by the G method of the flutter module in 0 is usually slightly higher than the lambda lowest and associated with a small non-zero frequency. The divergence of the free structure is so-called divergence, dynamic divergence. So now, how can we invert? How can we invert this matrix? We can invert this matrix only when the matrix is a square matrix. So then we have a so-called determined and overdetermined trim system. The total number of unknown trim degrees of freedom and trim variables equals the number of trim degrees of freedom, and then this equation can be solved by directly invert the left-hand side matrix. This equation is called the determined trim system. For example, if I want to solve uh, the trim analysis, perform trim analysis for aircraft at the 1G cruise condition. So I have a two trim variable. One is the angle attack. Another one is horizontal tail deflection angle. Then I have two trim equations. The first equation is the NZ. The NZ equal to 1G. The second trim equation is that the pitch acceleration must be 0 in order to satisfy this 1G cruise condition. So I have two equations, two unknowns, and the unknowns is angle attack and the horizontal tail deflection angle. So this is a determined trim problem. I can solve. I can by inverting this matrix. So this matrix become a 2 by 2 matrix. I can solve the determined trim problem. If the total number is less than the number of trim degrees of freedom, this trim equation is called the underdetermined trim system and is unsolvable. Again, if I want to perform a trim analysis for a 1G cruise condition, if I lost my horizontal tail, I only have angle attack as a one trim variable. I cannot solve this equation. So this is a so-called underdetermined trim problem. If the total number is greater than the number of trim degrees of freedom, this trim equation is called overdetermined trim system. To solve the overdetermined trim system requires the minimization of an objective function and while subjected to a set of a constraint function. For example, if for the aeroelastic active wing, and it has a 4 control surface on each wing, so I want to find out what's the best control surface deflection of those 4 control surfaces in order to maximize the roll rate. Meanwhile, the hinge moment of the control surfaces cannot exceed a design value. So this becomes a constraint, and maximum roll rate becomes the objective function, and the design variable becomes the deflection angle of the 4 control surfaces. Another example, if I have a joint wing, which under a 2.5G pull-up condition, the joint wing has 3 control surfaces on each wing. So I want to find out what's the best control surface deflection of those 3 control surfaces under 2.5G pull-up condition, and the objective function is that I want to minimize wing root bending moment, and also the control surface deflection angle must be within upper and lower bound. So this becomes a constraint, and this minimum wing root bending moment will become an objective function, and the control surface deflection becomes the design variable. And we want to compare the ZONAIR trim module with the next-gen trim module. And the ZONAIR trim module employs the modal approach, whereas the next-gen trim module uses the direct method. So if based on the modal approach, the size of the trim matrix, which is a fully populated and asymmetric matrix, is the number of modes for the modal approach, and is the number of A-side degrees of freedom of the next-gen direct method. So if we use 100 modes, and the size of the trim matrix is 100 by 100, whereas the A set of the structural model usually is very large. It could be over 100,000. So if you want to solve such a big matrix, it takes a lot of time. For a large finite element model, no more than 100 modes are sufficient for the modal approach. to converge. Whereas solve such a large trim, however, to solve such a large trim matrix by the direct method requires a large computational time. The ZONAIR trim module is capable of dealing both determined and overdetermined trim system, whereas the net trim module can only handle the determined trim system. For asymmetric condition, for asymmetric configuration, which is the symmetry of an XZ plane, ZONAIR trim module only requires a half-span structure model and aerodynamic model, even for asymmetric trim condition. So if you have a half-span and a structure and aerodynamic model, even you have asymmetric trim conditions. For example, you have alpha, you have beta. Internally, the ZONAIR trim module will decompose the asymmetric trim condition to a symmetric asymmetric trim condition to a symmetric trim condition and anti-symmetric trim condition. And then after we ZONAIR solve the unknown, then of the trim symmetric trim variables and the anti-symmetric trim variable, you can superimpose those solutions back to give us the asymmetric trim variables. However, the natural trim module always requires a full span model for asymmetric trim condition. And often people ask us, the static aeroelastic analysis is a static problem. Why the mode shape are involved? Okay, we use mode shape as a set of shape functions. The deformation of the structure is assumed to be superimposed of a set of shape functions. Because the mode shape satisfy the boundary condition of the structure, they are the best shape function. For example, if I have a cantilever wing, for a clamp boundary condition at the root, the mode shape satisfy the displacement and the slope to be a zero at the wing root, and the curvature at the wing tip to be zero. So all the mode shape satisfy this boundary condition. Therefore, they are the best shape function. The common misunderstanding of the modal approach versus natural direct method for static aeroelastic analysis is that the modal approach depends on the mass distribution of the structure model, whereas the natural direct method does not. This is a misunderstanding. For a free structure, the flexible aerodynamic stability derivatives computed by modal approach is nearly independent of the mode, as long as the center of gravity is invariant. Okay, because the inertial relief is required for the free static aeroelastic analysis, the mass matrix is involved in both the modal approach and the natural direct approach. Thus, if the CG is unchanged, the solution of both modal approach and the natural direct method change. If the CG change, okay, because for the free structure, the stiffness matrix is singular. So you cannot directly, even you use the direct method, you cannot directly invert that stiffness matrix. Therefore, even you use the natural and direct method, and you have to it involves the so-called inertial relief. Okay, therefore even the direct method depends on the mass matrix. However, if all structure in the structure all masses in the structure model are scaled by a factor, therefore the CG is unchanged. The flexible aerodynamic stability derivatives of both modal approach and the natural direct method are unchanged. So we're going to show you an example in the next slide. For clamped structure, the solution of the modal approach is independent of the mass matrix. Any mass matrix gives the same flexible aerodynamic stability derivatives. Okay, so we we give you example. This is the forward swept wing, and so it's a free structure. Uh, if we this nominal mass and this natural frequencies of the structure, based on this structure, we calculate the flexible stability derivatives of CL alpha and CM alpha, which give us this number. And if we multiply all the masses by zero point 0.1, so the natural frequency increases because we all the masses are scaled by zero point 0.1, so the CG is unchanged. You can see the flexible stability derivatives are unchanged. If we multiply all the masses by a factor 2, the natural frequencies reduce, and however, because the CG is unchanged, the flexible stability derivatives are unchanged. Okay, now for the clamp, if we clamp the structure right here, and then if we only perturb the mass at 100 and 112, okay, 112 and 100. 112 and 100. If we add change the mass here, so the CG change, but because it's a clamp one, even we calculate the flexible stability derivatives. You can see they are unchanged. Okay, so in other words, if you don't have a rigid bonding mode, even we use modal approach, the solution is independent of the mass matrix. If we have free structure, as long as the CG is unchanged, and no matter the even we change the mass matrix by applying a factor, the trim solution is unchanged. Next, we're going to talk about the optimization problem for solving the overdetermined system. The general optimization problem can be formulated as the minimizing the objective function and subjected to the constraint function. X is a design variable which is unknown trim degrees of freedom and trim variable. And ZONAIR requires the user to define a set of trim functions which we call which is a function of unknown trim degrees of freedom and trim variable, and such as section load, grip point displacement, force and moment, stress strain, aerodynamic forces, and the moment. The trim function can be selected as an objective function and a constraint function. So once you have defined the trim function, you can use the trim function to superimpose several trim function as an objective function, and also you can select the trim function as a constraint function. Okay. Meanwhile, you can set the so-called set constraint. So the unknown trim degrees of freedom, unknown trim variable, become the so-called design variable, and you can impose the upper and lower bound of those design variable. And some trim function requires additional input using this assigned matrix executive control command, or DMI data card. For example, if you want to calculate the inertial force, we need to import the MGG matrix using assign matrix executive control command. Once we have MGG, the trim module can calculate the inertial force. Okay, now if you want to calculate the element stress, in NATRAN, when you perform the modal analysis, you can ask NATRAN to output for a select element. You can ask NATRAN to output the stresses due to each mode. So NATRAN will treat each mode shape as a deformation and to calculate the induced stress at the elements. And so you have 10 modes. NATRAN will calculate 10 modal stresses. And you can import those modal stresses using so-called DMI card or assigned matrix card. So when once the trim module solve the generalized coordinate of the elastic mode, and it can calculate the stress in a select element. Now we're going to talk about the bulk cards. Of course, the required bulk card is called trim. Trim card is referred to by the trim case control card. And then the next one we have to have is called trim card. You have to define so-called trim variables, and we have other card to define object function and constraint function and so on. And also you can use a plot trim card to generate the net and force and moment cards after the trim module solve for the trim load. And also you can use plot trim card to output the deformed aerodynamic model, and also the pressure coefficient after the trim module solve the trim problem. So the major card is called trim, and which is referred to by a case control a case control command called trim. So this integer match with this ID, and you can use the plot trim card to output the force and moment cards, and also to look at the deformed aerodynamic model. Okay, and the trim card refers to aerogen card. The aerogen card defines the mean flow condition. Okay, all the alpha, beta, and control surface deflection defined in the aerogen card give us the so-called the aerodynamic force at the mean flow condition. Of course, you can use when you use aerogen card, you can replace the ZONAIR computer rigid CP at mean flow condition by a CFD compute CP distribution, or measured by the wind tunnel using CP spline or IMP CFD or IMP CFD1. So you can replace ZONAIR computed aerodynamic forces or pressure at the mean flow condition by CFD or wind tunnel measured data. And the next, you need to define trim variable. And the trim variable, we have three different kinds of trim variable. The first one is called program assigned trim variables, or control surface type of trim variables, or the next one is user defined trim variable. And the trim vector, for each trim vector, we need to calculate the aerodynamic stability derivatives of this trim variable. For example, angle tap. And also, and the trim vector can refer to a trim IMP. You can again you can use a CFD computer or wind tunnel measured distribute CP to replace the ZONAIR calculate the derivative of the aerodynamic pressure coefficient with respect to this trim variable, and for the rigid aircraft. In this case, all you ask ZONAIR to do is to flexibilize those stability derivatives. Or if you have if you want to link two trim variables together, there's a card called trim link card. And okay, if you have a overdetermined trim system, you have to use the trim obj card to define an objective function, and use the trim con card to define a set of constraint functions. And also, the trim card refers to a set1 card. The set1 card you can list off a set of trim functions for printout. So after the trim module solve for the trim problem, and you will based on this trim function to calculate the solution of the trim function. The trim function can be defined use as a section load. Use a load marker, or you can use DMI card to define say element stress as a trim function. Also, you have overdetermined trim system. You have to define trim OBJ, trim concar, and those two cards also refer to the trim function. In other words, you can use the trim function to define a objective function and the constraint function. And we have trim add card. You can add several trim functions together and to define a new trim function. So the trim card, the first is trim ID, which is referred to by the trim case control command. An ID arrow refer to the arrow gen card, and thus in this arrow gen card, you define the mean flow condition, and that's why you define a Q infinity, which is dynamic pressure. If you have a overdetermined trim problem, you have to define a trim OBJ and the constraint function trim concar, and the rho x, rho y, rho z is the XYZ components with respect to a vector from the aerodynamic moment center defined in the arrow z card and to the center of gravity. Therefore, the CG is defined by REFX, REFY, REFZ defined in the arrow z card plus rho x, rho y, rho z. So you specify rho y, rho x, rho y, rho z here. And the WT mass, if this is the weight, okay, if the weight, the WT mass is to convert weight to mass. So WT mass is 1 over g. If in the arrow z car, if the length unit is in inch and g is 386 inch per second squared, so this WT mass is 1 over 386. And the weight is the weight of the aircraft, and Ix, Iyy, and those are the moment of inertia of the aircraft with respect to the CG. And the TRNACC either true or G. If you say true, all the units in the NX, NY, NZ, P dot, Q dot, R dot are in true unit. If you say G, and those is specified by in terms of acceleration, the G. NX, NY, NZ are the trim degrees of freedom, and it's a translational acceleration along the XYZ axis. And you have three choices to define NX, NY, NZ. Either none. If you say none, this trim degrees of freedom is excluded from the trim problem. Okay. If it's a free, then this trim degrees of freedom is unknown. If put a real value, then this is a given trim degree of freedom. P dot, Q dot, R dot are angular acceleration. So also you can define as a non-free or real value. So for example, if I want solve for a 1G cruise condition, and then we as a none for NX, none for NY, P dot as none, Q dot as none, and NZ as is specified as a 1G. If this here I define G, then all I have to do is say NZ equals 1.0, and Q dot the pitch acceleration to be 0, so I put a 0.0 here. Okay, so I have a 2 trim degrees of freedom. And the low set refers to a set 1 car. The second card refers to a trim function card, and in the trim function card, you can define a trim function, and so when ZONAIR solve the trim problem, then you can calculate. Sorry. Then you can calculate the solution of those trim function. After that, this trim card is open-ended card. You first refer to the ID of a trim bar card, and the value you can define is either free or real value. For example, if I want to solve the 1G trim condition, and I put NX NY P dot R dot to be none, and NZ equals 1G, and Q dot equals 0. So I have two trim degrees of freedom. Then I can define, say, angle tag and control surface deflection to be free. So I have can solve this wedge cruise condition. So the unit of the dynamic pressure must be consistent with the length unit defined in the LZ count. And to compute the distributed initial loads of a free structure, you have to define the support entry in the assigned FEM. So to tell ZONAIR that you have a rigid body mode. And then you have to import MGG matrix. The aerodynamic forces and the flight condition defined by the aerogen are treated as the mean flow condition. So one of the trim variable is called thickant. The thickant represents the mean flow condition defined in the aerogen car. The IX, IYY are defined here. It should be noted that those weight and inertia must account for two sides of the aircraft, even if you only use a half span model. Okay, so this must be the mass matrix of the whole aircraft. If the NX if the trim degrees of freedom, if you define as none, then its associated degrees of freedom of the 6 rigid body motion is eliminated from the trim system. The remaining degrees of freedom are defined as the trim degrees of freedom of the trim system. Among these trim degrees of freedom, if free is specified, then the associated degree of freedom is defined as the free trim degrees of freedom. If it's given value, this is a given trim degrees of freedom. Also, for the trim variable, you can define as a free or given. Okay. So next one is the trim marker. Trim marker defines a trim variable for the static aeroelastic and the trim analysis. The ID is referred to by the trim car. And you give a label. For the label, you have three choices. First one is a program assigned trim variable. So you can put label equal to alpha or beta, P ray, Q ray, R ray, or thickant. Okay. Once ZONAIR sees the label equal to alpha, it understands this is the angle tag. Okay. And the unit is in degree, and beta is a side slip angle. The unit is in degree. P ray is a low ray, and which is non-dimensional. Is a PB over 2V. And Q ray is a pitch ray. It also is a non-dimensional longitudinal stability derivatives. R ray is yaw ray, and is normalized by the RB over 2V. Is a lateral stability derivatives. And thick can is the mean flow defined by the aerogen car. And also you can use CFD or Winslow measure distributed CP to replace ZONAIR computed mean flow condition and defined in the aerogen car. Okay, where the B, C are the reference span and the reference core defined in the LZ car, and the the longitudinal stability derivatives we call it partial CD by partial trim variable, partial CR by partial trim variable, partial CN by partial trim variable, and so on. And the aerodynamic force and moment coefficients is defined by those equations. So the first set is called program assigned trim variable. So once you define label equal to those characters, the trim module understand they are the program assigned trim variable. Now the second one is control surface type of trim variable, and if the label here match with the label entry in the LZ car or in the AE serve Z car, AES link, and PZT mode, and those car label, and you understand is a control surface type of a trim variable. And the if Zhongyi found out the input label does not match none of the program assigned trim variable and none of the control surface type of trim variable, and you understand this is user defined trim variable. Okay, so for example, you can define thrust as a program user defined trim variable. And where the DCD, DCY, DCL, and so on are the aerodynamic stability derivatives with respect to this trim variable. The default is none. If it's none, then you will internally compute those stability derivatives. Okay, you also can replace ZONAIR compute stability derivatives by the user supplied value, okay, of the rigid aircraft. Then ZONAIR will flexibilize those stability derivatives. However, if the label is a user defined trim variable, you have to import to specify those stability derivatives. And upper, lower and upper are the lower bound or upper bound of the trim variable. They are active. They are active only for the overdetermined trim problem. Trim link refers to a trim link car. You can link this trim variable to another trim variable. And the DMI you can import the DCP by D trim variable through this card. So DMI and you can either using a sign matrix or DMI car to replace ZONAIR compute DCP by D trim variable of the rigid aircraft by the user supplied values, or the DMI can refers to a trim IMP car. Okay, and in trim IMP car, you can define two set of CP at two different trim variable, and ZONAIR will use finite difference to calculate DCP by D trim variable. Okay, we're going to talk about the trim IMP car later. Okay, and trim link car if you want to link one trim variable with another trim variable, so in the trim var, you can right here you can refer to the ID of the trim link car. How do we use? Why we want to use the trim link car? For example, for fighters, and you have so-called control surface scheduling, and based on wind tunnel or CFD compute, they can find out at the leading edge and the trailing edge deflection angle become a function of angle attack. So so in this case, the control surface deflection angle is linked with the angle attack. Okay. So I can define a trim car, okay, as a angle attack, and another trim car as a leading edge flap, another trim car as a trailing edge flap, and in the angle attack, I can in the angle attack trim car, I can refer to trim link car, and in the trim link car, I can refer to the trim ID trim car of the leading edge flap and the trailing edge flap as a function of angle attack. Okay, and trim IMP is to replace the program computer pressure derivative of the trim variable by the user supply value. So this is referred to by the trim car, and then you have IMP CFD1, IMP CFD2, and CFD1 is a negative integer referred to IMP CFD, IMP CFD1, IMP DMI, and CP spline, CP spline L at A1 condition. Another set of those input pressure at another value, and so ZONAIR will use this equation to using the finite difference method to calculate the DCP by D trim variable. For example, if I want to replace the DCP by D alpha computed by ZONAIR by the user by the CFD computed CP. So if I have a CP at 1.5 degrees and another CP computed by CFD at 1 degree, so the A1 here will become negative 2, and A2 become 2. So I can use this equation to calculate the pressure derivative with respect to angle attack. And trim function, and you have ID, and you give a type. The type is either is aerodynamic quantity, or the trim function is related to the finite element model, or model is trim function is evaluated based on the so-called user supplied model data, and the label. If type equal to arrow, you can select the aerodynamic force and moment coefficients as a trim function. So you have induced drag, side force, and lift, and rolling moment, pitching moment, yawing moment, and the center of aerodynamic pressure, and all the trim degrees of freedom, trim variable, and sectional load or component load. if the type equal to FEN, you can use define and label becomes you can select low mark 1, which refer to a low mark car, and in the low mark car you can define a component load, or you can define a grid DSP is a grid point displacement. And if type equal to model, you can refer it to AFAC car. The model data is specified the AFAC car. The ID number of AFAC car for the symmetric or asymmetric model data is specified by the IS set, and for the anti one is defined by the IA set, and so you can also import a matrix using the DMI or assign matrix executive control command. And the right hand side, if you have a half span model, if I define, so I say type equal to FEN, label equal to Loma car, and then this IS set refer to the ID of a Loma car, and in the Loma car I define the wing rule bending moment. Okay, but if I have a half span model, if the trim condition is asymmetric, so the right hand side and left hand side wing rule bending moment will be different. So right here I have two choices. I can specify right hand side or left hand side. That means I want to calculate the wing rule bending moment at the right hand side or left hand side. This we use this only for a half span model. Okay, and okay. So this trim function car is referred to by the trim obj and trim con to construct objective function and constraint function. Also, it can be referred to by a set one car. The set one car is referred to by the trim car. In the set one car, you list the ID of several trim function. So after the Zhongyi solve the trim problem, you will calculate the trim function value, okay, defined in those set one car. Okay, the sign of the component loads is defined in the structure finite element basic coordinate. That is specified by this entry in the arrow z car. Okay, in other words, so-called the wing rule bending moment. And if your structural model and the area model are in different coordinates, so the component load is defined in the finite element model, not in the aerodynamic model. Okay. Next, trim add car is you want to define a trim function as a function of other trim functions. Okay, then you can construct a very complicated, a complex trim function. Trim obj only is used when you have an overdetermined trim problem, and so you have a this is referred to by the trim car. Then you refer to a trim function car, and then you use this C1, S1, E1, and so on based on this equation to construct. You can select several trim function to construct an objective function, and then we want the overdetermined trim problem is that to minimize this objective function, and trim con is defined a constraint function, and this one is also referred to by the trim car, and thus you refer to the trim function, and you can use S and E to construct a constraint function. And here you have two choices: is greater or less than a value. So using the trim car, you can define a constraint function. The last one is plot trim car. In the plot trim car, the ID trim is ID of the trim car. Flex is either you want to calculate a flexible one or rigid one, and the type you have force. If you have choice of force, if type equals force, and ZONAIR will output the trim loads in terms of natural force and moment cost at the structure fine element grid point. The user can insert this file into the natural model for detailed stress analysis. If equals CP, you can store the distributed area and pressure coefficient to a file. And deform, if you can plot the deformed aerodynamic model, if this is so you use the deform to plot to look at the deformed aerodynamic model, including the rigid body mode. If you put elastic, you will exclude the the deformation of rigid body mode only to plot the structure deformation due to elastic mode. So the next one we call symmetric, anti-symmetric, and asymmetric condition. ZONAIR can solve the trim solution of an asymmetric condition even a half-span model is used. Asymmetric trim condition involves both longitudinal and lateral trim degree of freedom. Both symmetric and anti-symmetric modes are required to be imported by the two assigned FEM executive control command. So in other words, the first one you set the boundary equal to sim. Another one the boundary equal to anti. The trim module superimposes the symmetric and anti-symmetric trim solution to obtain the asymmetric trim solution. So in other words, if you have a half span structure and aerodynamic models, you import the so-called symmetric mode and anti-symmetric mode, and you define a trim condition is asymmetric. So ZONAIR will split the asymmetric condition into a pure symmetric trim condition and another anti-symmetric trim condition. You will use the symmetric mode to solve the symmetric trim problem. Use anti-symmetric mode to solve the anti-symmetric symmetric trim problem. After that, ZONAIR will superimpose those two solutions, giving you asymmetric trim solutions. The symmetric trim condition involves only NX, NZ, and Q dot. Okay, and so only those trim vectors for the longitudinal aerodynamic stability derivatives can be selected, such as alpha Q and the symmetric control surface deflection, and only need a symmetric mode. So if I only want to solve a symmetric trim condition, if I have I only allow to use NX and the alpha Q and the symmetric control surface. If the trim condition is anti-symmetric, I only allow to select beta, P, and R, and anti-symmetric control surface. And I only need I need to import anti-symmetric mode. That is only for a half span model. If I have a full span model, and I can use all the trim variables and trim degrees of freedom. So this is the plot trim car, and you can look at the deform aerodynamic model. Also, you can output the trim loads in terms of natural force and moment cost. Okay, let's take a break, and then when we come back, we talk about some example. Okay, now we're going to talk about some sample cases for trim analysis. We use the so-called forward swept wing as an example. And first, we want to define several control surfaces. And the first one, we use the A sub Z car and refer to define a canal. Okay, it's right here. Canal is a symmetric control surface. And the CID refers to a core to our car. the y-axis of this quad car is the hinge line of the canal control surface, and ZK refers to the appendage 3 car, and which define lists out the panel ID of the canal. The second one we call aileron, and which is anti-symmetric control surfaces. It refers to a quad car. In the y-axis of this quad car is the hinge line of the aileron, and this define a panelist 2 car, which lists out all the panel ID on the aileron. So in other words, this is a half-span model. For if we define a symmetric control surface, when this control surface deflects in the mirror image side of the control surface, also deflect symmetrically. If we define anti, like aileron, if this aileron deflects upward in the mirror image left hand side, the aileron will deflect downward. And also we can use the same panels, but we call the trinage flap, which is a symmetric one. And so we can same set of panels can be defined as a symmetric or anti-symmetric control surface. And finally, we have a rudder defined here, which is an anti-symmetric. It refers to a quad car. The y-axis of the quad car is the hinge line, and we use panels 2 to list out all the panel ID on the rudder. It should be noticed that we can if this CID is a negative integer, then we use the z-axis of the quad car to define the hinge line. And so it turns out, well, later on we find out it is much easier to use the z-axis of the quad car to define a hinge line. And in the executive control section, because it's a half-span model, and later on we're going to do an asymmetric flight condition, so we need to import the symmetric mode and anti-symmetric mode. You're using two assigned FEM equals executive control commands, and then we need to import an MGG matrix. In this sample case, we import so-called SMGH and AMGH matrix, but instead of using two assigned matrix executive control command, all we need to do is to use one assigned matrix equal executive control command and import MNAM as MGG. So you can get MGG matrix from, say, Nation, and internally the ZONAIR will multiply MGG by the symmetric mode and anti-symmetric mode to obtain SMG and AMGH matrices. And we have to define solution 1, because in order to do static aeroelastic analysis, we need a spline, and so we have to define solution 1. The first sample case is a asymmetric rolling pull out at the Mach number 0.9, dynamic pressure equals 1200 psf, and we define 5 trim degrees of freedom. We want the side force to be 0, NZ to be 4.8 G. We want pitch, roll, pitch, and yaw acceleration to be 0. And we define 10 trim variables. The first one we want to define given aileron to be 25 degrees. So when we under this flight condition, when aileron deflect 25 degrees anti-symmetrically, you will induce a roll rate, which is which is the raw. Let me see the P rate. We want to find out what's the low rate we achieve. And meanwhile, we want to say, okay, in order to satisfy P dot, Q dot, R dot equals 0 and NY equals 0 and NZ equals 4.8 G, we want to define rudder to be free, beta to be free, and the canal to be free, and P rate to be free, alpha to be free, R rate equals 0, thickness is 1, and trim flap equals 0. So we define 10 trim variables: aileron, rudder, canal, trim flap, thickness. Thickness is the mean flow defined by the aerogen car, and this aerogen car is it refers to a Mach car. The Mach car defines the Mach number to be 0.9, and then we have a angle tach to be 1 degree, beta to be 0, and we have canal to be -1 degree. So this defines the mean flow condition and specified by the thickness trim bar car. Okay, this is the trim box cars. 100 is referred to by the trim executive control command, and the IDMK referred to the aerogen car, and the dynamic pressure equals 1200 psf. Because we have a 1, 2, 3, 4, 5 trim equations. We have a 1, 2, 3, 4, 5 unknowns. So this is a determined trim problem, and so we don't need to define objective and constraint functions. And the CG of this forward swipe model is at 17.27, and so rho x is 2.276, because in the Aero Z car we define the reference x to be 15. So the CG is 15 plus 2.27, and this is the CG. And the NZ, the CG at Z axis is 0.031. So we define 0.031 because IFZ is 0. And the weight is even this is a half span model, and for the weight must be the total weight of the full span model, which is 1,610 pounds. And this is in pounds. And then we want to convert the weight to mass, because the length unit is in feet. So the G is 32.2 feet per second square. So 1 over G is 0.03108. Okay, and to convert the weight to a slug. Then this entry with a G, that means all the trim degrees of freedom are specified in terms of G. So we have a NZ equal to 4.8 G, and then the true unit will be 4.8 divided by WT mass. So this is a true unit, and then we say nx equals to none. So we exclude this trim equation, which is along drag direction, from the trim problem, and ny to be 0, nz to be 4.8 g, p dot, q dot, r dot to be 0. So we have 1, 2, 3, 4, 5 trim degrees of freedom, and we give a canal to be 25 degrees, and we have 5 free trim variables. So we have 5 unknowns, 5 equations. So this is a determined trim problem. And meanwhile, in this entry, we low set refer to a set 1 car. In set 1 car, we list out the ID of 4 trim functions, So after when we solve for the trim problem, you will calculate the values of those trim four trim functions. And because it's a determinate trim problem, we don't need to specify trim obj and trim concat. And what's the four trim function? First, we are interested in knowing what's the hinge moment of the right hand side aileron. So we define a trim function car at equal to 10, which is referred to by the set 1 car, and the set 1 car is referred to by the trim car. And this belongs to the aerodynamic quantity, and we want to define a low Mach 1. And because this is a half span model, and under the asymmetric flight condition, so the loads on the right hand side and left hand side are different. So we want to say, I want to calculate the right hand side hinge moment. How do I define a hinge moment? It refers to a low Mach car, and this low Mach car refer to a contour car. In the contour car, I want to say the y-axis of the low Mach car. I want to calculate the hinge moment. And 2000 refers to a panelist car. And in the panelist car, it lists out the panel ID on the right hand side aileron. Also, 105 refers to set 1 car. It lists out the grid ID on the aileron. Okay, so this will define the hinge moment of the right hand side aileron. And the next one, I want to calculate the bending moment of right hand side wing. Likewise, this is belong to a finite element quantity, and I also refer to a low Mach car. In this low Mach car, ID is 101, and I refer to x moment, which I take a moment, take a moment about the x axis to calculate the bending moment of the wing, and 1100, it refers to a core to our no, it refers to a panelist car. In this panelist car, it lists out the panel ID on the wing, and also this one refers to a set 1 car. It lists out the grid ID of the wing and specify because here I specify right hand side, so we will calculate the bending moment of the right hand side. And another trim function is identical to the this one, except I say LHS. That means I want to calculate the bending moment of the left hand side wing. The last one I define type equal to model, and it refers to a DMI car. The DMI car on the right hand side, it refers to the DMI car called S bar 110. I want to calculate stress at C bar 110. Okay, and then I list out the modal stress due to symmetric mode and at this in this element, and also I import the anti-symmetric modal stress due to anti-symmetric mode, and list out here. Okay. So after first, then we will calculate the longitudinal and lateral aerodynamic stability derivatives. So this column is drag, this is side force, this is lift, this is rolling moment, pitch moment, and yawing moment. And thick cam is the mean flow, which is induced defined in the aerogen car. So for example, under this aerogen car is angle tag 1 degree, cannot equals -1 degree. The aerodynamic the lift due to the mean flow is printed out here. This is for rigid, this is for flexible, and you will calculate E over R, and this is the pitch moment. And next one is the aerodynamic stability derivatives of the CL CM with respect to angle tag. So this is per degree. For example, DCL, D alpha for the rigid is 0.088, for the flexible is 0.143, and this is E over R, and this is the pitch moment. Q rate is the pitch rate, and also so this will become DCL by DQ rate, DCM by DQ rate, and the unit is 1 over QC over 2V. And canal, because in the A sub Z car we define canal to be a symmetric control surface. So this is the DCL by D delta, D canal, and it's 1 over per unit degree. And next one, you print out the lateral aerodynamic stability derivatives. In the it should be noticed that even we have a half span aerodynamic model, all the force and moments printed out here are for the full span. So the lateral one, first one is beta, and so you print out dcy by d beta, d rolling moment by d beta, d yawing moment by d beta. This is p rate, r rate, aileron, because in the A sub Z car we define aileron to be an anti-symmetric control surface. This is the rudder. So we print out the longitudinal and lateral aerodynamic stability derivatives. And then you will use those aerodynamic stability the derivatives plus the thickness to solve for the trim problem. First we print out the value of the 5 trim degrees of freedom. Nx equals 0, Nz equals 4.8, Peta Qeta are 0. These are the user input specified values. Then you will solve for the 9 trim variable. Some of them are the user input, and some of them are computed. So any trim variable in the trim bar car defined as free, in the output you will say computed. Okay, if it's given one, for example, canal 25 degree, and it will print out canal as aileron to be 25 degrees. So aileron to become a user input. Okay, you will print out the flexible value and the rigid value of the trim variable solutions. After that, you will calculate the total aerodynamic force and moments, and this induces drag, this is the lift, this is the pitch moment. Okay, so the solution shows that in order to achieve a rolling pull out at n equal to 4.8 g, and this Q rate, the trim variable must be, because for the flexible one, the angle attack is 0.759 degree. But however, in the aerogen car, we define angle attack to be 1 degree. So actually the total angle attack is 1 plus 0.759, and the canal is a 4 canal is 4.775 minus 1 degree, because in the aerogen car we define canal to be -1. Okay, and the beta equal to -1.1 degree, p rate, and this the rudder. So using those, if we define the trim variable to be those value, and that will satisfy ny equals 0, nz equals 4.8, Peta Qeta R to be zeros. And after that, the trim module will print out the modal coordinate solution of the symmetric mode and anti-symmetric mode, and it will print out the result of the trim functions. Because we have a 5 trim function, we print out the flexible value, the rigid value. Okay, the next sample case is a symmetric level fly with 2 control surfaces. we want to satisfy a 1G cruise condition, and we want to use three trim variable: angle tag, canal, and trailing flap to be free. So we have two trim equations and three unknowns. So this become a overdetermined trim problem. So we need to define a objective function, which is trim obj, and we this one we refer to a trim function call. In the trim function call, we select induced drag. So therefore, we want to minimize the induced drag, and also we want to define a constraint function. Say the absolute hinge moment of the Trinity flap must be less than 900, and so we use trim concar, and the 10 it refers to the trim function call, which defines the hinge moment, and we use we define here. This is the hinge moment on the right hand side aileron. Uh, okay, then we take the square. Okay, we take the square, so we're less than 900 square. So this is the value. So we have a trim car, and we refer to the ID trim OBJ, which ID equals 10, trim car, which ID equal to 20. Okay, and then we have the same weight, and then we only see if NZ equal to 1, Q dot equal to 0, other trim duration freedom to be none. So we have two trim equation, and we have a canal and trim edge flap and angle tag to be free. So we have 1, 2, 3, three unknowns and two equations. So this is overdetermined trim problem. And so the program first will print out the objective function, and for the flexible aircraft, and this the induced drag. So the function value. So we can minimize the induced drag for the rigid one, and this for the flexible one, and also you print out the constraint function. This constraint function for the flexible one is this value, and this value is less than that value. So it satisfies the constraint function. For the rigid one, it also satisfies the constraint function. And then you will print out the trim solution. And the thick cam is user input, and alpha canal trailing flap are computed. This is for flexible. This is for rigid. In other words, under this condition, when n is equal to 1, and alpha canal and trailing flap, it can satisfy the 1G trim condition. Meanwhile, you can achieve a minimum drag condition. In this section, we're going to show you how to use trim module to obtain the critical loads of a generic transport aircraft. Identifying the flight conditions where the critical loads occur is the first step to generate the distributed loads for such a design. Critical loads usually are defined by selecting several loads monitoring points, such as the wing root bending moment, shear, and torque, as well as the fuselage section loads. The load marked by the car are used to define those loads monitoring points. The load marked by the car computes the component loads due to the net loads between the aerodynamic and inertial forces. FAA requires that the maximum and minimum loads factor for a commercial aircraft be 2.5G and -1G respectively. At a given angle tag, a given Mach number, search for an altitude where the maximum and minimum component loads occurs at 2.5G and -1G requires multiple trim analysis. And wind tunnel measure CP can be used for computing the component loads of a rigid aircraft. The static aeroelastic effect can be included by the ZONAIR trim module. The wind tunnel measure CP at various angle tag are used to search for the angle tag where the 2.5 G and negative 1 G occurs. So typically for twin engine aircraft, the shear, bending moment, and torque are selected as at the locations. For example, at the wing root where the largest bending moment occur, and the outboard of the pylon where the inertial load due to the pylon engine are excluded. So because the inertial loads created by the engine and the pylon, it's a negative load. So if we go across the pylon, all the loads will have a discontinuity. So the loads here will be higher than the and loads at the inboard of the pylon. So we select 3 points, and at each load monitoring point, we have a shear, bending, and torque. So totally, we have 9 component loads. And then we use the 9 load marker to define those component loads. And so we have trim car. In the trim car, it refers to a set 1 car. In the set 1 car, we list out the 9 trim function ID. Each trim function ID refers to a load marker to calculate those 9 loads. If we want to generate a diagram like this by varying angle tag, and we can calculate the load factor at different altitude at a given Mach number. So for example, if we specify angle tag 5 degrees in aerogen car, and we define and we specify the Mach number to be 0.7 and angle tag to be 5 degrees, and if we have the wind tunnel measure CP at this Mach number and this angle tag, we can use the CP spline to interpolate the wind tunnel measure CP to the ZONAIR panel model. Then we specify NZ equal to 3. We want to calculate for a given angle tag. We want to calculate the load factor, and we impose at the pitch oscillation to be 0. And then we use another trim car to and so we want to use the elevator to achieve Q dot to be 0. So this trim car is this one referred to the aerogen car, and this the dynamic pressure at a given altitude, and this defines the CG, and then this because this is the 1, so because this WT mass equals 1, so those mass are in true unit. And then we specify we only have a 2 trim degrees of freedom. First, NZ equal to 3, and we want to impose Q dot equal to 0, so we have 2 equations. And then we have a 2 trim variable. One is a thick cam, equal to 1. One is the elevator equal to 3. So we have a 2 trim equations, which is NZ and Q dot, and we have 2 free. So this is a determined trim problem. So and we have to specify solution 1, and we have to import the natural model solution using a sign FEM, and we have to perform spline to activate the static aeroelastic analysis, and then we repeat this process for various angle tag and dynamic pressure at each altitude, and so we refer to the aerogen. In aerogen, we change the angle tag, and then we replace the ZONAIR compute CP at this angle tag on region aircraft by wind tunnel measures CP. So finally, we can generate at each angle tag, we can calculate the NZ at a different altitude. Then, so for each altitude, and we can find where at which angle tag it can achieve 2.5 G at each altitude. Likewise, we can find at which angle tag we can achieve the negative 1 G. And then after we generate that, we can plot the 9 loads. The first one is at the wing root, the torque, shear, and bending moment. At on the elbow of the pylon, have a torque, shear, and bending moment. At elbow wing, we have torque, shear, and bending moment. So for 2.5 G, we intersect with this guy, and we found a corresponding torque, corresponding shear, and the corresponding bending moment. And at another altitude, we also find the corresponding torque, shear, and bending moment. So we do the same thing for the pylon and elbow wing. And then at the Mach 0.7, 2.5 G, we can list out all the value, the wing root torque, shear, and pylon, and elbow wing, and so on. And we found that the maximum value for each component load. And this is at negative 1 G, and we found out the maximum or minimum loads. Okay, so then this is at this Mach number, and then we can change to another Mach number and repeat the same process. And after we finish all the Mach number and all the altitudes, we can find out which one is the maximum or minimum. So that is so each lowest monetary point will give us each critical loads. So we have 9 critical loads for 2.5 G, 9 critical loads for negative 1 G. So that will give us totally 18 distributed loads, and we can give that to the structural people to do structural design. And finally, we can use the plot trim car to output the loads in terms of net strength, force, and moment cost. And then we summarize how to compute the critical loads, and we want to use wind tunnel or CFD data to create CP and AIC database on rigid aircraft. That's the first step. Step 1, at a given flow condition in terms of Mach number, angle tag, side slipping angle, and number of control surfaces, we can use the CP spline or CP spline L to interpolate the wind tunnel CP or IMP CFD or IMP CFD1 car to map the CFD CP to the ZONAIR model. And then we can further adjust the CP by the match LD car. Remember, in the wind tunnel, we can measure the component loads, but even we interpolate wind tunnel CP or CFD computer CP, we use those CP to calculate the component loads like wing root bending moment. It may not match with a wind tunnel directly measured wing root bending moment. So we can use this car to further adjust the CP in order to match the wind tunnel directly measured component loads. Then we can save the CP, adjust CP. You use the plot CP car form equal to output 4. Okay, we can save this into a file in output 4 format. And then the next step is we want to correct AIC using wind tunnel component loads or CFD component loads or CP. You're using WT1 AJJ or WT2 AJJ. And we also can save the correct AIC by the output 4 car. The AIC matrix consists of 3 matrices: AJJS, FJKS, and DKJS. So we use the 3 output 4 to save those 3 matrices. Step 3, if the wind tunnel CP, CFD, wind tunnel measured or CFD compute CP are on the cruise ship, we have to use the jig ship and jig CP to correct the CP, to adjust the CP on the cruise ship to the jig ship, and resave the CP using the plot CP card with entry form equal to output 4. Step 4, we repeat step 1, step 3, step 2, and step 3 for different Mach number, angle tag, and control surfaces. And we create a CP database. We create an AISC database. And then we use the CP and AISC database to perform accurate trim analysis. Step 1, for performing trim analysis, for example, at a 2.5G pull-up condition, we guess a set of alpha na, beta na, delta na that nearly satisfy the trim condition and specify them in the aerogen card. Then we import the CP and AIC of at those alpha na, beta na, and delta na using assign matrix executive control command. And we can use IMP DMI to replace ZONAIR compute CP by from the CP database. So we can either use assignment matrix or we can use the IMP DMI card. If the trim solution in terms of delta alpha, delta beta, and delta delta are not small, the select alpha na, beta na, delta na in step 1 are adjusted by alpha na equal to alpha na plus delta alpha, beta na equal to beta na plus beta delta beta, delta na equal to delta na plus delta delta, and we repeat the step 1 and using the trim IMP to replace ZONAIR compute CP derivative. For example, DCP by d alpha by referring to two IMP DMI card. The first DMI card is at alpha plus epsilon 1. The second MP DMI is at alpha minus epsilon 2. So it will compute the trim MP card. It will compute the DCP by d alpha using a finite difference method. Step 3, use the Loma card to output the component loads computed by the trim analysis, and the plot trim card to output the trim loads in terms of net strain, force, and moment card. Among all flight conditions, if one of the component loads is the most critical one, all critical loads flight condition is determined. The corresponding trim loads are used for stress analysis. Repeat step 1, 2, 3, 4 to find all critical loads flight conditions for all component loads. Okay, that's the end of the this section.